Hi, I'm John Pace, a member of the R.M. Santilli Foundation and the chairman of this World Lecture Series on Hadronic Mathematics, Mechanics, and Chemistry. It is a pleasure and honor for me to introduce you to Professor Ruggiero Maria Santilli, who will present the need, history, and foundation of the novel isomathematics that is necessary for the consistent treatment of the Lie-Santilli isotheory of the preceding Lecture 2A. The study of isomathematics was initiated by Professor Santilli in late 1977 at the Department of Mathematics of Harvard University. Additional important contributions were made by the mathematicians Professor Myung, Professor Arangasan, and Professor Karashvili, and numerous other scientists identified in the original literature, all available in a free downloadable PDF in the attached Word file. Studies of isomathematics were then continued from September 1981 on at the Institute for Basic Research located at the Prescott House, which is within the compound of Harvard University, as you can see from the map. For the record, Professor and Mrs. Santilli purchased the Prescott House in mid-1981 to house the Institute for Basic Research and continued the administration of various DOE contracts. The inauguration ceremony was held on September 8, 1981, with the attendance of scientists from various countries. 2 international meetings were then held, the 4th workshop on Lie admissible formulations and the 2nd workshop on hadronic mechanics. Research on isomathematics was then continued from June 1989 to present time at the new location of the Institute for Basic Research in Florida, where the institute was moved. Professor Santilli made a basic mathematical discovery, that of new numbers today known as Santilli iso, Gano, hyper, and isodual numbers, when he was a visiting professor in 1993 at the Joint Institute for Nuclear Research in Dubna, Russia. The final obstacle in the achievement of maturity for isomathematics was resolved by Professor Santilli in 1995 at the Institute for Basic Research in Italy, then located at the Castle Prince Pignatelli in Monterudini, with the discovery of the novel series of calculi known as Santilli iso, Gano, hyper, and isodual calculi. The discovery occurred jointly with an international conference on hadronic mathematics, physics, and chemistry, attended by over 150 participants from 50 different countries, which conference resulted in over 3,000 pages of proceedings. The understanding of this lecture requires a technical knowledge of the mathematics underlying Lie's theory, including fields, manifolds, functional analysis, differential calculus, and topology. This lecture is part of a series based on Lie-Santilli isotheory and includes the preceding lectures 1A, 2A, and the subsequent lectures 3A, 3B, and 5A. Ladies and gentlemen, it is my distinct pleasure to introduce you to Professor Santilli.
Ladies and gentlemen, today I will present the needs, the history, and the foundation of a new mathematics called isomathematics, which is necessary for the consistent treatment of the Lie-isotopic theory presented in the preceding lecture 2A. Let me indicate that isomathematics has been the result of advances made by numerous very distinguished mathematicians. Among them I should mention Professor Myung. He was my co-author in the lifting, as we in our language, the isotopy of the Hilbert space and a number of other structures. I should also mention Professor Arangasan from Kazakhstan and Professor Karashvili from the Russian Georgia, that essentially initiated the so-called isofunctional analysis. It is also a pleasant duty to remember the unforgettable Professor Tsagas, chairman of the Department of Mathematics at Aristotle University in Thessaloniki, Greece, and his associate Professor Sorlas. They introduced the notion of isomanifold and made truly intriguing advances Additionally, I should mention Professor Nunes and Professor Ganfornina from the mathematics department of University of Seville in Spain, who formulated one of the central mathematical tools of the entire series, which goes under the name of isotopology. We will have time to illustrate the fundamental character of those studies. I should also indicate that there are a number of books now dedicated to isomathematics, or at least to branch of isomathematics. Here I have a few. For instance, I would like to bring to your attention a book by the mathematician from Beijing, China, Professor Jiang, who wrote a book on the foundation of the Santilli isonumber theory. It's a truly fundamental book for this series because everything is based on generalized numbers, as we will see. Also, there is a book by Professor Tsagas and Professor Nick Sorlas on the Santilli Lie-isotopic theory. There is a book by Professor Kaitishvili, published by the now called Vadunka in Kiev, on Santilli isotopy of relativities and so on, but most of it is a review of isomathematics. Perhaps the most rigorous formulation of isomathematics is in this book by Professor Nunes and Ganfornina from Mathematics Department, the University of Seville. As I said, it is in Spanish, but it is definitely the most rigorous presentation of isomathematics, and this title is Lie-isotopia de Santilli. Also, I have two volumes on my own. The volume 1 of Elements of Hadronic Mechanics also presents essentially the content of this lecture in more detail, but its intent is also to approach theoretical physicists. So it is mostly in applied mathematics more than in pure mathematics. All these books, as well as the original papers, are available in free PDF download in the Word document that joins the title and the original link of this lecture. Very well, let's get started. There are today many definitions of isomathematics. I'm sure the mathematician will present in this series a very rigorous definition. As far as I'm concerned, I have selected a definition that is accessible also to theoretical physicists. So I shall define isomathematics as the lifting, in our language, which is essentially broadening if you want, the lifting or broadening of the totality of the mathematics underlying Lie theory, therefore including number, functional analysis, differential calculus, topology, etc. All this mathematics has to be lifted in such a way to admit as the left and right unit at all levels the most general possible integral differential entity, operator, or matrix if you want, that is solely restricted by the condition to be positive definite, but otherwise it has a completely unrestricted and arbitrary dependence on any variable that you want. This is a crucial point for this entire series, to have the unit that has an unrestricted functional dependence. You will see many applications on this point alone. Now, if you lift the associative product the way we did in the preceding lecture, namely, excuse me, by sandwiching the inverse in between the elements, then it's very easy to see that that this arbitrary entity now is called nowadays Santilli's isounit, or just isounit in this lecture, is indeed the correct left and right unit at all levels. Very well, let's see now why there is the need of this new mathematics. There are so many mathematics in the mathematical lecture, as I'm sure mathematicians will agree. Well, the answer is that the need of this mathematics is specifically physics, because of very specific physics needs and requirements. To see the need, first we have to review what I called the majestic axiomatic consistency of Lie theory, and therefore the majestic consistency of the formulation based on Lie theory, such as special relativity and quantum mechanics. The essence, in my view, of this majestic construction is that at the classical level, Lie theory and related physical formulations characterize a canonical transformation. At the operator level, this formulation characterizes a unitary transformation on a Hilbert space defined over a field of complex numbers. As you know, both a canonical and unitary transformation leave invariant the basic unit or a unit matrix. This is extremely well known, so well known that appears trivial. Well, ladies and gentlemen, it's far from being, the implications are very, very deep. And therefore, those properties, those basic properties are far from being trivial. Let's review some of them. From a mathematical viewpoint, this implies that the formulations here considered leave invariant the basic unit of the basic field. And this invariant persists at all times or on any action of the group itself, symmetries, and so on. This is by far non-trivial. This means that the base fields remain valid and therefore applicable at any time. And this is an illustration of what I call a majestic consistency, because it holds not only under a Polaroid picture at the initial time, but the consistency remains at all subsequent times. From a physical viewpoint, the implications are equally deep. The unit that is treated from an abstract viewpoint by mathematician, from a physical viewpoint, it represents the unit actually used in measurement. Of course, the representation is abstract and realization free. Let's consider, for instance, the unit of the Euclidean space is diagonal 1, 1, 1. Well, that's mathematics. From a physical viewpoint, this is a very deep meaning. It implies diagonal 1 centimeter, 1 centimeter, 1 centimeter. Not only this sets the unit of measurement, but also is established homogeneity and isotropy from this very, very ultimate and most fundamental pillar of the theory, the unit. And those, as you know, homogeneity and isotropy are at the foundation of special relativity and 20th century theory. Additionally, it's very easy to prove that under those assumptions, the theory here predict the same number under the same conditions at different time. This is explain my word majestic consistency. Moreover, it's easy to prove that those theories preserve hermeticity, therefore observability at all times, etc., etc. Those remarks illustrate the reason why the 20th century theory do have indeed a fully deserved towering position in history. Very well, let's go now to a broader theory. Any theory to claim any degree of novelty over 20th century theory must be non-canonical at the classical level and non-unitary at the operator level, because those conditions are necessary to exit from the class of equivalence of 20th century theory. Indeed, for instance, the quantum mechanics has indeed very broad class of equivalence called a class of unitary equivalence that incorporates many, many different theories claimed to be generalized, instead they are not. However, when the broader theory is non-unitary, then it's certainly outside the applicability of quantum mechanics. Indeed, hadronic mechanics was being conceived to be non-unitary, precisely because it's necessary for the representation of the synthesis of the neutron in the core of a star from a proton and electron and many other physical problems that we want to investigate. Now, however, by conception, a non-unitary transformation or a non-unitary theory does not preserve the basic unit. This has catastrophic consequences as far as the consistency is concerned, mathematically and physically. The word catastrophic may be objected by some of the colleagues, but it is now has been used in several referee journals, and it is now part of the folklore, where you are referring to the so-called theorems of catastrophic mathematical and physical inconsistencies of non-canonical and non-unitary theories when formulated with canonical and unitary mathematics, respectively. Very well, let's see from the mathematical, what happens from the mathematical viewpoint. Well, by definition, the basic unit of the basic field is not conserved over time by non-unitary theory. Ladies and gentlemen, this is truly catastrophic, because this implies that if a field is fully consistent at the initial time, at the subsequent time, that field has no meaning whatsoever, not anymore, because it has lost the unity, has changed. Now, once you have lost the basic field, the totality of the mathematical structure collapses, in my view, as well as in the view of a number of refereed publications. So indeed, we are talking about a catastrophic collapse of the entire mathematical structure. This illustrates a reason why the broadening of 20th century theory simply cannot be treated with the mathematics of the 20th century, because otherwise you end up with all sorts of inconsistency. In any case, you have no hope of preserving their beauty and consistency. Very well, let's go now from a physical viewpoint. What happened at the physical level? Well, the consequences are truly catastrophic. First of all, a non-unitary transformation does not preserve the basic unit used in measurements. So therefore, the theory cannot be applied to measurements. So therefore, at this level already, I have no interest whatsoever, none. Unless we can confront our theory with measurements, I don't think there is any physical relevance that will pass the test of time. But that's only the beginning. Notice, not only will we lose centimeter, but here, if here is 1 centimeter, here there is another unit, here is another unit. Therefore, under non-unitary transformation, you lose the homogeneity and isotropy that at the very heart of the geometry of 20th century theory. So you have very serious and very deep consequences, as we will see also in subsequent lecture. Moreover, it's very easy to prove that under non-unitary transformation, you cannot predict the same numbers under the same conditions at different times. So if you predict 42 seconds of precession of perihelion at a certain time, at a later time you may have an arbitrary number. And incidentally, this is typically of Riemannian geometry, which is a non-canonical theory. And is one of the aspects that is ignored in gravitational studies, to my best knowledge. We will address it in a special lecture dedicated to gravitation. Additionally, there is another point that has to be brought to the attention of interested colleagues, and is known under the name of Lopez Lemma. It is a property that is identified by Professor Lopez in Dubna, in one of the meetings in Dubna, I believe in 1992 and 1993, and essentially it states that the hermeticity is not necessarily or otherwise generally conserved under a non-unitary transformation. That is, if you have an operator such as the Hamiltonian, which is Hermitian at the initial time, then you apply the system to a time evolution, and that the image of that Hamiltonian under time evolution is not necessarily Hermitian. Loss of hermeticity implies loss of observability. Therefore, again, you have a truly catastrophic collapse and consequences at both mathematical and physical level. Now, remember, hadronic mechanics was proposed to be, by conception and construction, to be a non-unitary theory, namely to be centered on a non-unitary time evolution. I proposed at Harvard University in 1978 as via the isotopy of the Heisenberg equation in their infinitesimal and finite form, which still now are at the foundation of the isotopic branch of hadronic mechanics. So it's clear that after identifying those catastrophic inconsistencies, then the hadronic mechanics was, the very, very survival of hadronic mechanics was at stake. So, but the hadronic mechanics was not the only one to suffer and verify the theorem of catastrophic inconsistency. There are many, many theories, because this issue has been virtually ignored in the 20th century physics, even in the best refereed journals, but not all, however. And however, the first theory that verifies those catastrophic inconsistency is one that I introduced myself. In 1967, I published a paper that was an essential part of my PhD thesis at the University of Torino that essentially introduced the PQ deformation of Lie algebras. Those are in both finite and infinitesimal form. It's very easy to verify that the finite time evolution is non-unitary. So therefore, you verify this theorem of catastrophic inconsistency squarely, directly, and fully. In 1986, Larry Bidner, a good friend of mine, the late Larry Bidner, in 1986 published a paper on the shorter version of those deformations, namely the Q deformation. Those deformations too verified the theorem of catastrophic inconsistency. Incidentally, Larry was fully aware of my origination of the deformation in 1967 because we applied for a grant, jointly for a grant at the Department of Energy, an application that incidentally was denied. The point is, however, that after Larry's article, there were literally tens of thousands of articles in Q deformation, none of which quoted my origination in 1967. And for this reason, I've been dubbed the most plagiarized physicist of the 20th century. I heard this dubbing several times by friends and people who care about honesty in science. But there was not a question of honesty. These people, they did not know the origination. Anyhow, I shall indicate that I never complain about these tens of thousands of papers who do not quote it to me. Why? Because they are inconsistent. And so I did not want to see my name associated to papers that I do not believe will resist the test of time. In any case, Q deformation are a very small and minute part of a particular case of hadronic mechanics that now has resolved those inconsistencies, and so therefore they can, all those papers can indeed be formulated in a consistent way. There are many, many other theories that verify this theorem of catastrophic inconsistency. For instance, I mentioned gravitation on a Riemannian space. This is a non-canonical theory. Also, quantum gravity is a non-unitary theory. Necessarily, if it is non-canonical at the classical level, must be for consistency non-unitary at the operator level. So you have all those inconsistencies, the Kac-Moody algebra, the supersymmetric algebra, and many others that I believe the physicists should perhaps give some look at the inconsistency and either prove them to be correct or disprove them, but disprove them in refereed journals and not via a nice conversation in academic corridor. In 1981, we inaugurated the Institute for Basic Research at the Prescott House that was located within the compound of Harvard University, but it was an independent institute of research. Soon after the inauguration, we had two meetings, one in mathematics and one in physics, and we had visitors from numerous countries. And I remember very, very exciting times, especially because of the intellectual independence of thinking, even researching and studying anything we want with no restriction of any type. That freedom was absolutely invaluable, at least to me. Okay, the central problem that was addressed since the first day of inauguration is how can we represent variational non-self-adjoint forces in an invariant way. Because if we achieve an invariant representation of the forces that are at the foundation of interior dynamical problem, then we had realistic hope of bypassing the theorem of catastrophic inconsistencies. Okay, that was not an easy task. It requires years of trial and error, many, many failures, never published, and so on. Finally, in 1983, I proposed the representation of variational non-self-adjoint forces via the generalization of the basic unit that I called the iso unit, as the inverse of the isotopic element that I had introduced at Harvard University in 1978. It soon turned out to be an excellent choice. First of all, from a mathematical viewpoint, the unit is the most fundamental invariant of any theory, whether conventional or generalized. So therefore, if we manage to embed non-self-adjoint forces or non-unitary effect or non-unitary interaction, if you want, or non-Hamiltonian interaction, if we manage to embed them and represent them with the unit, invariance is guaranteed, because the unit will not be changed. So there was, indeed, we looked for years for any better alternative. We could not locate no better alternative than representing non-potential forces with the basic, with a generalization of the basic unit. No other hypothesis or proposal turned out to be even minimally comparable to the ISO unit. If there is any different view, this is a fundamental point. I strongly recommend colleagues to publish their view in refereed journals. Very well, so, but this set already from 1983 set the very, very foundation of everything that we will do throughout this entire series. Namely, we will represent conventional self-adjoint interaction with the conventional Hamiltonian. Hamiltonian remains completely unchanged. So anything that you think about Hamiltonian, of course, Lagrange remain unchanged. Now, the novelty is that all non-potential non-Hamiltonian interaction and effect are represented with this integral differential operator or matrix. We will have many illustrations throughout this entire series, but I believe it's important to flash few simple illustrations right now, so that the theoretical physics can have a grasp of the mathematics that is about to follow. From at the level of interior classical system, we prove that this type of exponential function, where f is an arbitrary function in the exponent, solely subjected by the condition to be positive definite, this representation allowed us to achieve universality for the representation of all possible variational non-self-adjoint Newtonian forces. So they have quite some power, but they had something more. Look at the isotopic element. Under this condition, this function is positive definite, then the isotopic element, which is sandwiched in between quantity and matrices, is definitely smaller than 1. This is non-trivial, ladies and gentlemen, because already from here you can see that the isotopic element can accelerate the convergence or even create a convergence when a series is divergent, as we will see. At the operator level, this very simple exponential expression of the ISO unit, in which basically you see on the exponent, you see a wave function, which is one of the most general possible form of non-linearity. Remember, we are interested in theory which are non-linear, non-local integral, and non-Hamiltonian. Namely, you cannot be solely described by the Hamiltonian. This is clearly a very nice illustration, because you see the very general form of non-linearity. Also, our version of non-locality. We are talking about non-local integral type of a structure. And also this allows us to represent, to recover quantum mechanics very easily when the wave functions do not overlap anymore, and the volume integral is 0, then hadronic mechanics recovers quantum mechanics uniquely and unambiguously with no possible misunderstanding. So in this sense, quantum mechanics is a particular case of hadronic mechanics, as we will see. Again, if this is positive definite, then the isotopic element is smaller than 1. And again, we are talking about the possibility of eliminating divergences in quantum mechanics. That's the Dirac's dream, as we will see later on in this lecture. So the promises were very serious, and therefore we had to dedicate a study of this type of theory that represents potential interaction with the Hamiltonian and non-potential interaction with the generalization of the unit. However, ladies and gentlemen, I am a physicist. To do any theory that can minimally satisfy me, again, has to be scientific. I've said this several times. We have to repeat it. We have to do a mathematical elaboration that produces numbers, and those numbers have to be verified with experiments. Ladies and gentlemen, the moment we generalize the unit, we lose all numbers. So therefore, the entire value collapses. In other words, at this stage of the investigation, there was no hope that hadronic mechanics will have any physical value on real, concrete term, the way I said, such to surpass the test of time. And the stumbling block that lasted for many years was mainly emotional, ladies and gentlemen. I had a simple devotion for the mathematician that achieved the classification of all numbers, the historical classification. As it is very well known, is numbers, namely sets that verify the axiom of a field, are classified. The only possible are the following, that was claimed in the literature of the 20th century, are real numbers, complex numbers, and quaternions, Hamilton. Octonions are not numbers because they violate the associativity of the law of the axiom of a field. I have listed only a few of the outstanding scientists, mathematicians, who worked at this classification, and I had simply a devotion of them, Cayley and so many others, and Hamilton and Moebius. Moebius is my genius and my mentor in topology. I had a great devotion of this, and so I assumed that this classification was indeed final, and therefore hadronic mechanics was just a dream at this moment. So, and this lasted for years. Finally, one day, out of sheer desperation, I was visiting the Joint Institute for Nuclear Research in Dubna, Russia, 1993. And as I said, out of sheer desperation, I said to myself, I got to have the courage to reinspect the historical classification of numbers. The moment I had that courage of questioning the historical classification, everything became very easy. The solution was practically instantaneous. Why so? Because an inspection of the axiom immediately revealed that there was no absolute need of assuming the number 1 as the unit of a numeric field. No, the axiom of a field do not restrict the explicit numerical value of the unit. They only require that the unit be positive definite. So if you have a positive definite integral differential operator, or the number 1 that dates back from Assyrian and other civilization 4,000 or 5,000 years ago, still used in the 20th century as the foundation of all mathematics. So from a viewpoint of the axiom, this integral differential operator, this 5,000-year-old number, are the same, are essentially equivalent. So, and indeed, it was then very easy to propose what today are known are Santilli ISO number, which I have shown you the book of by Professor Yang from China, as well as many other publications now in several fields. Basically, what is the idea? Well, in a language that is accessible to theoretical physicists, suppose you have an ordinary conventional field or number, namely where A can be real, complex, or quaternion. And suppose that you have a positive definite arbitrary entity outside the original field, And then you construct a set of this entity called isonumbers, which are the product of the ordinary number multiplied by this entity, which is positive definite. And then here is the main point. The set of those entity called isonumber, when you reserve the conventional sum, but you equip the set with the isomultiplication, then it's a very useful exercise that I recommend to everybody who has not been exposed to this type of studies. Then it's very easy to verify that all axioms of a field are indeed verified. It is a very interesting exercise for colleagues, both mathematicians and physicists, who are new to this type of studies. In fact, it's very easy to prove that the set contains an inverse, careful, the iso inverse, defined in accordance with the rules of the iso field. Also, the isosum is the conventional one, so it preserves the isocommutativity and the isodistributivity of the conventional sum. The isoproduct is isoassociative, but not necessarily isocommutative. And then the set of isonumber is closed under all possible combinations of the various operations that we have indicated so far. Conclusion, the isonumbers are indeed essentially new realization of the axiom of a field that had escaped, essentially had escaped the attention of mathematicians for centuries. That's what is in reality the case. Santilli's isonumbers are today classified also as isoreal, isocomplex, and isoquaternions. In addition, there is a classification into two groups that does not exist for ordinary number. Namely, isonumbers are called of type 1 or of type 2, depending on whether the isounit is an element of the original field or not. So, because we have a possibility, the isounit can be the number 37.254, or it can be an integral, or can be the exponent that you have seen before. It's very easy to prove that isofields are locally isomorphic to fields, namely they are fields. In reality, at the abstract level, you lose any distinction, to such an extent that I have seen recent paper by mathematicians that I indicate here because they may represent kind of a threat to other mathematicians not familiar with this, in which those mathematicians they present isonumber with all conventional terminology, symbols, and everything is as for ordinary numbers, but they mean something dramatically broader than the number 1, 2, 3, 4, or the complex number, something extremely much more broader. And so the only thing is reduced to in a fine line with a characterization of the unit that is much broader than the ordinary number. So those papers are insidious for mathematicians who are not familiar with those advances. A very important subclass of isonumber is the type 1, when the unit is an element of the original field. In this case, suppose you have isoreal, the isounit is an ordinary number. Positive, carefully, positive definitely. And then it's very simple to prove this lemma that in this case, for type 1 isoreal, the set of this set in which you essentially the isonumbers are given by ordinary number without any need of multiplying them by the isounit. This subset of isofields are also fields. They also verify the axiom of a field. But then the consequences, ladies and gentlemen, are not trivial. Let me give you a glimpse. Suppose I wake up one day, as I did, and I say, I'm tired of using for a basic unit the number 1 with 4,000 or 5,000 years old. There has to be some form of generalization. So one day I wake up and say, okay, I want to use for unit the 1/3. This is my basic unit of the basic isofield. Fine. Then 2 multiplied by 3 certainly is no longer equal to 6. It is 2. And the number 4 is prime. The number 4 is prime. So the implications for number theory are indeed very serious. As a matter of fact, a number of mathematicians have to be alerted in their interest that some of their papers published in the best mathematics journal are not truly perfect from a mathematical viewpoint. For instance, the statement that the number 4 is not prime is not mathematically correct anymore. The mathematically correct formulation is that under the assumption of the number 1 as the basic unit of the field, then the number 4 is not prime. But if you throw just the statement the number 4 is not prime, this becomes nowadays as no longer a mathematical meaning and should be revised accordingly. Very well. Here, very quickly, I flash you the reason why some addition cannot be lifted in our language. I don't have time to enter. This was published in the original paper of the isonumber in 1983. This is explained in all details. There is a violation of the axiom of a field. Remember, I am a physicist. I have to do experiment. I need numbers. I have to verify the axiom of a field. Otherwise, I'm not happy, and I have to look for something else. Okay, here are some of the consequences. Well, the most important consequence, what I discovered out of sheer desperation when I was in Dubna, in the middle of this nuclear physics laboratory, thanks to a very nice hospitality by colleagues there that I would like to indicate, I visited Dubna in Russia. Well, immediately after the collapse of the communism, my wife and I, we were among the very first to go to Russia because we had many friends. We were received by former President Gorbachev for a private 15 minutes, very nice conversation. I've been the guest of Moscow State University, Dubna many times, Protvino, and I have many friends in Russia. I have no words to say thank you for all this hospitality to beautiful Russia. Incidentally, I wrote to Russia a number of very important, for me, very important papers. This is only one of others, very important. But I hope I will have time in other lecture to bring them to your attention. But the discovery out of sheer desperation was the axiom of a field do not require that the basic unit be the pre-biblical number 1. Can be any entity, provided that it is positive definite. We will see in other lecture that this positive definiteness will be removed. In this case, we have broader numbers, so-called Gannon numbers. And then, not only that, but we have isodual number for antimatter. And then when the unit has multi-value, we have the hyperstructural formulation of hadronic mechanics. Everything based on generalization of numbers. Each branch of hadronic mechanics allowing, indeed, experimental verification, because it admits real, actual numbers verifiable with experiments. Another point which is important to bring to the attention of the audience is that from an abstract viewpoint, there is no difference between numbers and isonumbers. Again, the isonumbers are nothing but a new realization of very old axiom of a field. This was intentional. I had no intention of changing the axiom of a field. I could not. Otherwise, I don't do physics, as indicated before. Then there are other implications that are intriguing. The last one I want to bring to your attention, namely application to cryptography. As you know, the bankers, sometimes they don't sleep at night because they're afraid that hackers will break the cryptogram protecting your and mine checking account, and therefore do all sorts of movement of money that this has occurred many times, unfortunately. Well, so the central objective of cryptography is to achieve a cryptogram that is not breakable, or at least is extremely difficult to break, namely to solve and allow hackers to enter into a system. Well, you should know that a cryptographic company in England has purchased the rights of isonumbers to create a new series of cryptograms that are based on a multiplication and therefore admit an infinite number of possible units. I repeat, those are called isocryptograms. They, by conception, they admit an infinite number of possible iso units. So the hacker has to locate one out of an infinity. It's not that easy. Besides, the cryptograms are designed in such a way that the unit can be changed automatically by the computer. So therefore, the cryptograms, isocryptograms, do appear to be indeed actually unbreakable in practical terms. Whether mathematically can be solved is a different issue. Unfortunately, I cannot disclose more because isocryptograms are very secret. It is possible that I can only say it is possible that some of your credit cards are protected by an isocryptogram and not by an ordinary cryptogram, because I can assure you are much more difficult to break than an ordinary cryptogram. This to give you at least a flavor that isonumbers are not just fancies or academic curiosity. No. They are far from all that. First of all, they have extremely serious implication in pure mathematics, particularly in number theory. But then the numbers are the foundation of all of mathematics. So their impact in all of mathematics has to be expected. From a physical viewpoint, isonumbers are fundamental. Without a generalized iso unit, we would have been simply unable to achieve the invariant formulation of interior dynamical problem with arbitrary internal interaction, and I will not be speaking to you here today. because the theory I would not have considered worth of presentation. It's just that simple.